So first, let's record for linear Navier-Stokes equation. We have psi alpha, so it's a stream function, and we take the alpha, so it's a horizontal Fourier transform of t, and y, which may be given by an integral over some contour of exponential lambda t. And what you have to put here is the inverse of the Sommerfeld equation. So R depends on alpha, on c and of nu of some inverse of the initial vorticity, so omega 0 alpha over a alpha. So the Sommerfeld is linked to the resultant of linear Navier-Stokes equation, which means that the solution of linear Navier-Stokes equation in stream function formulation is directly given in terms of the inverse of the Sommerfeld equation. And so the Sommerfeld equation reads, so this is the transport and time derivative of the vorticity minus us prime prime psi minus epsilon second derivative equals 0, and this is of course the Laplace of omega, and epsilon is something like nu over a alpha. So this is just linear Navier-Stokes equation, just in stream function formulation, and alpha is, so I should put an alpha everywhere, of course, but I will soon forget. Yeah. And so we have boundary condition, which is that u at y equals 0 may vanish, and u is a gradient perp of psi, which means that psi of 0 equal dy psi at 0 equals 0, and psi should go to 0 at plus infinity. Okay, so this is Sommerfeld equation. Of course, here you have the Rayleigh equation. So this is Rayleigh part. So Sommerfeld is Rayleigh plus diffusion, namely Navier-Stokes is Euler plus diffusion. So no problem. So then you have two cases. If you look at some shear layer profile, you have two cases. So the first case is you have no eigenvalue, no unstable mode. No unstable mode. The mode for Rayleigh. So this is the case, for instance, if US is monotonic. So if, for instance, US prime prime is always positive, like for instance 1 minus this, so a wave profile. So the farther from the boundary you are, the you are, then you have no more. So this is the first case, and in this case, a spectrum from Rayleigh. So we are in the C space. So C is turned by the factor A with lambda. So you know that you have some continuous spectrum, which is there, which is a range of US, and you have no eigenvalue. So this is for Rayleigh. Other case, you have something which has an inflection point. This, and you see that this is unstable, and you can see that in fact you can make a rearrangement of the various layers in order to preserve all the quantity except that the energy, which will be better. You can make a rearrangement to have this kind of thing, and it's unstable because it gives some more extra energy. So this is unstable for Rayleigh. And then you have a growing mode, which is psi of Rayleigh, and a growing mode, which is growing with some C of Rayleigh. And of course, you have some alpha. For some value of alpha, you have an unstable one. And the velocity, corresponding velocity, is gradient perp of So now I put the, so it's E alpha x minus C T psi ray of alpha y. So you have an unstable mode which is explicit. So you see that you have made a Fourier transform here, and you have made a Laplace transform here. Of course, you have that. So in physics, people write the C because here you see the kind of velocity which comes here. Not a problem. And of course, it's unstable, meaning that the imaginary part of C is positive. So there is a minus, you multiply by I. It gives you a growing mode. And psi is a solution of Rayleigh, namely US minus C dq minus alpha q psi Rayleigh equal from S psi Rayleigh. And psi Rayleigh 0 equals 0. Then the space is as follows. You has a so part of the range of US where the Rayleigh equation is not well defined, it's not resolved, and you have so eigenvalues with speak the most unstable one, C ray. So when you look at that, if you look at this kind of profile, what you get? So you have your shear layer profile, and what you get is there is a unstable mode which will grow. So let's put some color on. So you will have some psi Rayleigh, which will be growing and growing. And so what you look at the beginning, the streamlines are like this. And when time goes on, you have this kind of instability which grows and which makes nonlinear things. And you end up with something like cat eyes lines for psi. So perhaps not up to this thing, but the flow then gets unstable with a periodic motif in X, and so the streamlines get from straight, and then you begin to have a cat eye picture. So this is for Rayleigh. Now what happens when you add some viscosity? So now let us look for Sommerfeld. Here you have no eigenvalue, so you have nothing to do. But what happens if you add some viscosity, and I will give you the hint just after, is that for small nu, then you can prove that there exists two eigenvalues which comes out of alpha equals 0. So there is one eigenvalue plus its conjugate, so one eigenvalue which comes out of alpha equals 0. So for alpha very, very, very small, namely for very, very long periods, then you have an unstable mode which appears in Sommerfeld, which is not in Rayleigh. So you have emergence of one eigenvalue, the corresponding instability, so alpha OS. So it's in the regime nu1 to nu1 So the wave number of the instability is extremely small, like nu1 corresponding to very large horizontal structure. And the corresponding C is of order nu to the 1/4 also. And which means that the product, in fact, lambda to the product is of nu1/2. So you have a kind of bifurcation out of nu equal and the onset of an instability, like for bifurcation, which is of magnitude nu to the 1/2, corresponding to very, very, very long periods in X. So you have the pictures as follows. You have like this, And what you have is instabilities, which turns out to be periodic, but the instabilities occurs on lengths of order nu to the -1/4. So I will describe them later. Before I go on with this direction, so in this case we have some eigenvalue here, and this is what Toan told you yesterday. If you add a small viscosity, then the eigenvalue will slightly shift. But basically, you can make a construction of instability of Sommerfeld out of instability of Rayleigh, and basically you have C of Sommerfeld is C of Rayleigh plus something like square root of nu. So you just have a small modification. However, the main modification that you have is that the derivative of Rayleigh is not 0 at 0. So this is the main annoying point, because your eigenmode doesn't satisfy this one. This is exactly what Toan told you yesterday. When you want to construct instability for Sommerfeld out of Rayleigh, so no problem because you will get it and it's very close. However, you have to take care of the second boundary condition, which is never fulfilled for Rayleigh, but should be fulfilled for Sommerfeld. And so the instability of Sommerfeld will be the instability of Rayleigh. So let us put some variables. So some y, which depend on y, plus another term which will catch up the boundary condition, and which will be a boundary layer of size y over square root of mu. Plus. So I will not detail again the construction done yesterday by Toan, except that to recall that we can construct instability of Sommerfeld starting from instability for Rayleigh. However, the instability for Rayleigh are slightly more complex, since now the picture is as follows. You have your profile, which is unstable. You have the profile for psi. Perhaps not too many structure, so let's see like that for psi. And then what you have to add is another corrector, which is psi or Sommerfeld, which will look like this, with something happening here over size over the square root of mu. So the picture of the instability has two different sizes, which is one, which is the size of your flow, and another one which comes from the boundary layer, which is Nguyen force. This is here. In X, the size of the perturbation is capital O of 1. The time of evolution of the growth of the perturbation is also capital O of 1. You are growing, and the perturbation reaches something like this of order 1, 2. So this is a case for when you have an eigenvalue, which is different from the case where you have no eigenvalue. Do you have question on this part, or is it clear? Sorry, not 1/4. Excuse me. Square root of mu. Thanks. Thanks a lot. Thanks. So now I will focus on this. So this has been done with Toan, and justification of that using generator method is done in a paper with Toan in Anal PDE. We will detail the first case. So let us look again at Sommerfeld. So we will have to describe the instability. It turns out that it's almost explicit. So yesterday I claimed that it's a first-order differential equation, so we have 4 different solutions, too fast and too slow. Let's just look at the fast solution first. So the fast solution. So there is plus and minus, which are supposed to have derivative. So we can main term. So there is a derivative in first term. So I simply rewrite our Sommerfeld equations, and there is first term. Then there is second term. In d2 psi there is plus us minus c. There is also plus 2 epsilon alpha square, which comes from here. And then we have terms with only psi, which are, we don't care. We see alpha square with a minus u prime prime s, we don't care. And we don't care of the minus epsilon alpha 4. This is just a rewriting of our Sommerfeld. Now it's fast solution. So for fast solution, these terms will be large and this will be small. So we focus first on this term, and we write Airy equation, Airy of theta, which is minus epsilon theta plus us minus c plus 2 epsilon alpha square theta. And the first thing is to solve this. We will solve this, we will make an error. We make an error here, and then we will iterate. We will solve it and iterate and solve it and iterate. So the first step is to construct solution of this. So first step, Airy of theta equals 0. If we linearized, then we have minus epsilon d2 theta plus us prime of yc times y minus yc theta equals 0, where us of yc equals c minus 2 epsilon alpha square. So there is a funny epsilon alpha square, but don't be too upset with that. It's very, very, very small, in fact. Just looking for the formula. Yeah, E alpha nu. So we define gamma to be E alpha us prime over nu to the 1/3, just to get rid of everything which is in front. And then we see that for this equation, we have a solution which is theta of y is the Airy function times gamma 1 minus yc. And the answer is not by, it's cy, where cy equals ay plus a by. It's the other Airy function. Take care that this is not a real number, because the argument is something like 1 over pi over 6. So this is not real, and this function is decreasing. So basically, it's like this. It's very rapidly decreasing, since it decreases like exponential minus y to the 3/2. So very fast, much faster than a derivative. And cy, so is the other one. And their Wronskian should be something constant. So first step, that. Second step, theta is dy square. So theta equals psi. So then we have psi, the first guess. So let us just construct the A1. It's A1 second primitive. So the 2 here for the second primitive of A1. In physics books, you have tables of the second primitive of A1. Okay, so this solves this. And of course, if you put into our Sommerfeld, it doesn't solve anything, because you have this equal psi. Well, this is but not important. This is small, because I is very rapidly decreasing, so this term is very small. So now what you define is psi2 such that area T2 psi2 equal minus this. And then you look at psi1. And okay, I think you have understood the procedure because this term is negligible with respect to this one. So the idea is to solve this one, you consider this as a perturbation and as a function as very rapidly decreasing. In fact, it's much faster decaying, so you have no problem. So at the end of the day, this gives you exactly a perfect description of psi minus. So psi minus a fast term of y is second primitive of every equation plus something which is small. So to simplify the presentation, I will look at alpha of order Nguyen force. And so you have a Nguyen force here. We could make all the thing between Nguyen force and Nguyen 6, but Nguyen force is the most instable one. And so you exactly have the value at 0, which is the area function second primitive. This gamma is explicit, it's there. And YC is explicit also because it's there, so it's directly linked to C. So it depends on C, of course. And you have exactly the same thing for the derivative. At 0, it's also explicit. So there's a gamma coming out, and there is a first derivative on YC. So which is pretty explicit, in fact. So next, you have slow modes. The slow mode is supposed to come from Rayleigh and supposed to have this decomposition Rayleigh plus Laplace. And so for you have two solutions. You have one smooth, which is given by an entire series. So for this, it's okay. And you have one non-smooth. So, but in fact, you are branching out of alpha equals 0. And for alpha equals 0, Rayleigh equation is nice, because for Rayleigh alpha equals 0, this is Rayleigh equation. So again, this is an equation you can give in exam, because there is a very simple solution, and the simple solution is psi. First solution is US minus C. So it's more than explicit. So for alpha very small, you know exactly what is a small solution. And the other solution is psi2 of y is US minus C, integral between whatever you want and y of u1 st minus c squared. So it's pretty explicit too, even it's a little less explicit. And interesting point is that you have a yc log y minus yc singularity of the critical medium. So now you have this for alpha equals 0, and then you have to branch out of alpha equals 0. Of course, when alpha equals 0, this goes to a constant at infinity. This is linear. We have no exponential behavior. But okay, we can make a computation. For alpha small, there is a crazy trick from physics. They introduce a crazy identity, and they are able to make the computation explicitly. And basically, what they get, so this is a pretty crazy things, is that they get the solution, and it is US of y minus c exponential minus alpha y plus something like alpha. So the physics which allows to track all the solution which gives a good prove it, because it's pretty technical. And so you know exactly US minus of 0, which is exactly minus C. So it's not exactly minus C, because then you have other things to add. You have to take care of the next term. So it's C plus U plus square divided by US prime at 0 plus something which is alpha square. You find this in physics books, made the computation. It's a long time, and you have dy of Cs minus of 0 equal US prime at 0. So here it's almost a proof. I think working a little you can do it. It's not a proof because there is a trick inside that is absolutely crazy. We are trying to write the detail down. So it will be soon posted, I think. But anyway, you have the complete description of the tube. Do you have some questions about that? So very, very explicit. Every function and just US. So now we can look at the dispersion relation. So we are looking for eigenmode. Namely, we are looking for a combination of psi s, psi f, which satisfies our Sommerfeld, so and the three boundary conditions. Of course, we have psi which goes to 0 at infinity. And so if we have a mode, then it must be a combination of the slow mode and the fast mode which goes to 0 at infinity. So any mode must be a combination of modes which go to 0, no problem. And of course, we must have psi of 0 equals 0 and psi prime, so dy psi at 0 equals 0. Which means that we must have the same link between psi s minus psi minus and the derivative. And so the dispersion relation can be written psi f minus of 0 equal psi s minus of 0 divided by psi s minus of 0. So this is the dispersion law. Because if we have this relation, then we can find B 0 such that the condition are equal. So this is the dispersion relation. So it's not a big deal. It's true for any 4 orders differential equation with 2 solutions going to 0 at infinity. Okay, so let us look at that with that. That basically I know. And this is a fast mode. So this is small because this is small because this is much smaller than that. And so this is of order 1 over gamma, which turns to be Nguyen 4. And this can also be very small if psi s minus of 0 is small, because this on the bottom is basically u prime. So basically it's 1 given. But this basically is this value, and so it can be small. Perhaps there is an alpha here missing, right? Alpha, sorry. So this can be small. This can be small. This is also of order Nguyen force if C is of order Nguyen force. So there is no contradiction. There is a possibility for things to be equal both times. And so then you can go on further and let me just make a picture. Then everything is explicit, because what you have here is some airy function. So it's airy of 2 minus gamma of yc over a1 of minus gamma of yc, 1 over gamma. Gamma is given here, and it should be equal to alpha u plus square over u prime s0 square minus c over us prime 0. And you have also a link between yc and c. Basically, yc is over us prime 0 plus something which is smaller. This is just the fact that us of yc is more or less c. So you see that you have this equation together with this equation. So you can read this. And it gives you C as an implicit function of alpha. So C given as a function of alpha. In the physics books, you will see the name of the function, which is here, which is called the Tietjens functions. Tietjens function is just basically it's a ratio between these two things here. Yeah. Okay, so now we have, everything is explicit. Psi is airy, integrated twice. Psi prime is airy, integrated 1. Gamma is given over there, is explicit. This at 0, it's that, it's explicit. US prime is 0 is explicit. U plus value at infinity is explicit. And dy is US prime 0, so everything is explicit. So you have an implicit function. So Tietjens of yc is given something like in alpha. And so then you can make a picture and you can compute the things. And if you look at the imaginary part of C, multiplied by nu1 force, as a function of the nu1 force times some constant alpha 0, then what you get is, here you have about 2, and you get is something, a picture like this. And here you reach something like 1/2. And the maximum is reached at about 2, a little more than 2, something like that. Basically, the picture. Which gives you that if there is some alpha 1, if alpha is larger than alpha 1 nu1 force, then there exists some C, which is order nu1 force, which imaginary part of C, which is positive. Namely, you have an unstable mode. So now we can even completely describe the unstable mode, because basically we have exactly the stream function. So the stream function, you can find also this in books, hopefully some part somewhere in the dressing and rate, which is, so this is explicit, this is US minus C times exponential minus alpha y. So there is also plus alpha u plus square over u prime s, but it's in fact it's very small, so I don't care. Plus, so some alpha, something like nu1 force times airy q of y minus yc plus nu1/2. And what I wrote for psi, you would differentiate term by term, and you have omega, and you have a dy psi. So what is the picture of that? The picture of the instability. So this is my boundary. So first you have yc, which is at nu1 force. So you have nu1 force, which is called the critical layer. That's why just before I said nu1 force instead of nu1/2. So you have a critical layer. In the critical layer, you have the airy function which enters into the play. So here you have a very complex flow. So it's described by airy area here. So you have the airy function which describes what happens there. It's on alpha very small, so it's very large structure in X, like Q minus 1 force. So it's periodic in X, but with very, very, very large periods. So it's very thin and very large. And above, it's trivial. Above, basically, it's US exponential minus alpha y. So it's some kind of displacement. And you see that there is another side which appears, which is alpha y equal 1. This new minus 1 force, which is a kind of recirculation layer. So in the critical layer, you have an interaction between the speed of the wave and the speed of the flow. And at this point, you have some kind of dispersive phenomena. You don't have mixing, I don't know how to say, but you have an interaction. And you have an interaction in this airy part where you have a boundary layer, which is kind of airy style here. And then above, you have just a bulk motion, which is linked to US, so it's kind of shift of US or something like that. And very far, then you have recirculation of the flow. So streamline should be something like that. But very, very, very spread in that direction. The spreading in that direction. So you have another side, Nguyen force, critical layer, which come from the airy part. And you see that almost everything is explicit in this computation. Do you have some question on that, or is it clear enough? Enough pictures? So now I'll go on with Sommerfeld and then go back to boundary layers. So we have four different equations. So we have written that in an IHP paper. You can construct the green function. Namely, it's a bit like for the relay, you have four elementary solutions, and then you can try to combine them to solve or Sommerfeld or green function equal delta at some point x. In fact, it's pretty easy because it's a 4x4 system to study J, but it has a very strong block structure, so you can do it pretty well, in fact. So now let us try to go with, let us go back to the frontal stuff. So back to frontal, so back to Navier-Stokes to Euler. Given some overview of relay, some overview of Sommerfeld, and now I go to Navier-Stokes to Euler, namely, let me rewrite the equation. So usual equation, of course, at y equals 0. And of course, I would like to understand what happens when u goes to 0. So as mentioned by Toan, first thing I would like to understand, first thing is in the case where u is constant away from the boundary, so you have Euler is constant, 1 direction, and so we are just looking at some shear layer profile. So in this case, the frontal layer is just a shear layer, and so we want to study particular solution which are of the form us of t y over square root of nu 0, where of course we have the heat equation on us. So basically this is frontal, and that is a very simple case where the Euler component is 1. So should begin by that. So this is square root of nu. So yesterday, Toan spoke of u, which with inflection points, where relay is unstable and makes the construction. It's somehow artificial because you have to assume that the boundary layer is bad. So probably it's better to assume that the boundary layer is some exponential or some Blasius. People who know Blasius, of course, you can pick up Blasius or some exponential one. But if we look at that, then as done previously, we can rescale time, space, and with respect to nu, so we can just make a blow up in all the direction. And of course, Navier-Stokes with viscosity nu becomes Navier-Stokes with viscosity square root of. So not much is changed, except that now in this rescale variable, everything has length 1. So then, so I have this, Euler, frontal, and what can I make? Make a zoom by a factor 1 over square root of nu. And so I am now with something like that. Square root of nu, 1, and here. Of course, I've done that. But now I know that this profile now has square root of nu instead of nu, but it's 5. But I have a fixed profile. I have a fixed profile, so it's 1 now. I have a fixed profile, which is US of t, so square root of nu t and y. I can forget for the time dependency for y because it's a longer time scale, so let us forget that. But what I know, if I replace by 0 to begin with, then if I replace by 0 as the first approximation, then I know that it's a fixed profile for orthogonal for nu small, so there is an unstable mode. So it's unstable, and there is an unstable mode with branches from 0 with alpha 1, which is the new viscosity is 1, which is nu 1, 1/4, corresponding with C1, nu 1, 1/4. So simply by rescaling, I am back to Navier-Stokes with a shear profile 1 here fixed. And so now when viscosity goes to 0, then you have some instability which comes out of 0. It's the classical things you can find also in physics books, of course. And I follow one of the possible instability, which is nu 1/4. And, but take care that alpha 1 is nu 1/4 and C1 nu 1/4. So here, nu 1/4. And I have structures in rescale variable which have nu 1 minus 1/4. Okay. So I said that I will make pictures, and I made a lot of pictures. So now I go back to the original variable, and what do I got? I have 1, which is Euler. I have square root of nu, which is frontal zone. And then I have nu 1, 1/4. So it's nu 1, 1/4 in original variable. So you have to scale back. So nu times square root of nu. And nu 1 is square root of nu itself. So nu 1, 8, nu 1/2. So it's nu. So you have a sublayer here, which is nu 3/8. This is linked to the so-called triple deck construction. And sorry? 5, yeah, sorry. Yeah, it should be smaller than 1. And in this side, then you are nu 1 minus 1/4 this time. Square root of nu, this time it's probably nu 3/8. No? Nu. You see that you have a double structures. because you have total, which is unstable, and which give birth to another one. So I will discuss the physics of this after, to relax. But before, I will go a little further. Except if there are some questions on that, of course. So this you can still find in some books, of course. Not exactly like that, and I will comment on it later on, because I don't say it's really physical. So, but now, now I can, okay, there is instability which grows. So it's life. So I have my field, U, which is the profile, plus something, an unstable mode, instability. I make it very small initially, and it grows like exponential lambda t. And of course, I forget all the, there's a complex conjugate and so on. Okay, so this is linear. And of course, the real part of lambda is of order nu to the 1/2. 1/2 or 1/4. This is, sorry. Yes, is nu. So the velocity is nu 1 minus 1/2. So the speed of growth is nu 1/2. And so this is square root of that, yeah. Nu. No, nu and force, sorry. Don't remember, not important. And so we have a very, very slow growing mode here. So we have basic flow, this is slowly growing mode. For in Toan's case, the previous yesterday, lambda was over the 1, so we have a normal growth. But here we have a slow growth. So what happens when we try to go on to the next order? Then, of course, we put this into Navier-Stokes, and there are interaction coming out of that, and the interaction are, so the interaction of U with itself, and they have something like this, so which is a source term. And so to go on, we have to construct a quadratic term, a cubic term, and of course other terms. It's a little more complex because then we have. Okay, so let us construct the cubic term. So the quadratic term. The quadratic term is a solution of linearized Navier-Stokes equation taking of UQ equal minus stuff. You have this kind of stuff. And then you compute the next one. So the linear Navier-Stokes on cubic is the interaction between the quadratic and the first order. I am a little fuzzy on this because there's many terms to write. But the idea is you have a linear perturbation. You put into the equation, you have a quadratic form term which comes out, so you have to correct it. So you again introduce a new term to correct the quadratic, and then you have the cubic, and then and so on, and so on. Exactly as done yesterday in Navier-Stokes when you construct the expansion up to any order. So let us look at x. Here, periodicity is A alpha x. So when you multiply A alpha x by itself, you have A plus and minus 2 A alpha x, because at 0 it always cancels for some reason. And then when you make the cubic terms, then you have again this, and you have, of course, third order harmonics. So when you look at this term, you see that if you look at first harmonic of alpha, then there is no first harmonic of alpha. But here you have again a term of alpha. What is its size? So at each term, you want to invert in a Navier-Stokes equation, namely you invert or Sommerfeld. So or Sommerfeld of 2 alpha of uq equal source term. So invert you this by or Sommerfeld. But of course, you are near the spectrum. So when you are near the spectrum, the resultant is bad, and you lose a factor distance of the spectrum. So basically, when you look at a matrix, the norm of the inverse is over the one of the distance to the spectrum. Basically, for single eigenvalues. So when you invert our Sommerfeld equation, then you lose a factor nu. So loss of nu minus 1/4. Go. So in Toan-Stokes, we were interested in the loss of derivatives because each time you make this operation, you lose one derivative, which is bad from a mathematical point of view. But here we lose some new factor, which is bad from a physical point of view. So basically, you have u equal u plus linear instability, which is so u instability exponential lambda t nu n plus quadratic correction plus cubic correction. So it's uq and quadratic and cubic. uq and uc are this. So this, we can start from an order 1. I don't specify the norm. Q is new to the minus 4th, and UC is new to the minus 1/2. So if you look at the expansion, you have, if you look at the exponential A alpha x things, then you have U alpha equal the instability this plus U cubic over nu exponential 3 lambda t nu to the 3n. And you see that these two terms are of the same magnitude when this is over the nu 1/4. Exponential lambda t nu 1/4 is of nu 1/4. Both terms are equal. Terms have the same magnitude. So this is no longer an expansion because the third term and the second terms are exactly the same. So, but in fact, it's very. It was awaited. It was awaited because we are in the context of a bifurcation. We are in the context of a bifurcation, and we have an eigenvalue which comes from nu equals 0. And which bifurcates like square root of nu. So we have nu equals 0, and we have some eigenvalue which behaves like square root of nu. And if you have looked at some bifurcation, you know that what is important is the first non-zero nonlinear term which drives the thing. So if you look in a very easy way at phi of t to be the size of the perturbation, then you have this kind of Landau equation on this, which is phi over dt equal lambda phi. And then you have to take care of the first non-zero term. Of course, here you see 1 and 1 gives 2. And then 2 minus 1 gives 1. So you have to get cubic terms plus some capital phi. So if you look at phi, the normal form or whatever you say of the perturbation is this one. Lambda is over there nu to the 1/4. So you see that the fate of phi will depend on the sign of A. Because then if you multiply by phi of bar, you have d over dt of phi bar should be something like a real part of lambda phi square plus A plus A phi square times phi square or something like that. I don't remember exactly. But it's the classical things in bifurcation theory. So what you have to look if you have something which is very, very small. Of course, if lambda is equal to 1, we don't care of that because we have an order 1 perturbation. We don't care. But if lambda is very small, then we have to know what is A in order to know whether our perturbation will grow or not. So what is A? Is projection on the unstable mode of the cubic interaction. So A is projection of the unstable mode. So let us call it phi in star. So it's the projection on it. So the projection on the unstable mode is the scalar product with the unstable mode of the adjoint of cubic interaction. Where this is a mode, eigenmode for the adjoint of orthomorphism. Adjoint of orthomorphism is a bit, for L2 product, is a bit like orthomorphism, except that you have now the Laplace outside, and that so it's a little more singular than orthomorphism itself, because instead of having y log y singularity, you have 1 over y instabilities for Rayleigh. And so this is a computation that you need to do. So you have the instability with itself, which interacts, which gives you a quadratic interaction. Then you interact it again with the instability. This gives you cubic interaction. And then you make the scalar product with the dual, and it gives you A. So this is explicit, except that you have to do it numerically because it's a real function, and so you cannot do any computation. So we have done this with Nguyen. So it's an archive now. And the answer is A seems negative. So the real part of A is negative. It should be a real part of thing. Yeah. A is negative. So A is negative, which means that you have a negative feedback from the cubic term onto the first one. This remains to be checked, and we are trying to make it another way by another method because it's fully computational. So we will do it again another way, purely numerically, in order to be sure. But it's quite natural that it's negative. Yeah.
What is the size of A?
A is over the 1 then. There is no size, yeah. It remains to study it on the whole spectrum between Nguyen 4 and Nguyen 6. There's a lot of things to do, but perhaps it can even vanish. But to know if a quantity vanished is delicate because it's numeric. So, but so it vanishes up to the numerical approximation. But in any case, you have many cases where A is negative. So what does it mean if A is negative? This means that we expect the instability in the sublayer to grow, but perhaps to stay bounded at Nguyen force. So conjecture. So instabilities which Nguyen force. So this is true. We have already done that with Toan, but not more, and not more. So this is a bifurcation problem. So we are trying to look at that with Mariana Auguste to try to know if we can put some theorem on that, and to try to prove that for particular initial data, then we can have these pictures, namely whole thing here, sublayer, so nu 1/2, nu 3/8, and then here some rolls which would appear. Very small amplitude rolls, very small amplitude rolls for that. Do you have questions, remarks on that? So at this point, what seems to appear is, let me just find the theorem here. What seems to appear is that you stop there because then you have an instability, and so probably it reaches Nguyen force. Okay. In physics, you can find these kind of things, and in particular in bachelor, you see that in 3D this gives birth to rolls, and yeah, a 5/8. Yeah, at this point, if it is rolls, then what you see in physics books is that you have rolls 3D, and then you can have horseshoe types instability, and you can have the rolls to enter into the domain and to become turbulent, which is possible. Yeah. So present time we will check that, of course, as a method, and then to look if a classical method can be applied from bifurcation theory. For sure, classical cannot be applied because there is no spectral gap. There is a very small spectral gap. So the usual method seems to fail, but we will try to go into that direction. So now let us go back to the case unstable, and then I will just comment the possible physics of that. So I go back now to the case Toan detailed yesterday with Euler, which is 1, but assume that we have taken something which is unstable. So of t and of y over square root of nu, which is unstable. So frontal layer here, Euler, which is 1, and some nasty profile of US with unstable. Then, as detailed by Toan, you have an instability, and the instability gives you this picture here. Just look at the true size. You have Euler, you have square root of nu. Then what you are doing is that you will have a sublayer, as discussed just below, which is nu 3/4, which is exactly what discussed Toan, because Rayleigh equation doesn't satisfy our Sommerfeld condition, so you have to add a boundary layer to your instability. So you have a sublayer. Okay, but let us play. Let us play again, because now we have something with its periodicity with the square root of nu. Okay, the instability Toan described was something which is periodic. So perhaps I should say this is something, so square root of nu here, square root of nu here. So if we are at the level of Euler, we have Euler, frontal, very small, and so we have instability like that, square root of nu, square root of nu. Now if I make a blow up to really see this, I have this. But now we have a sublayer which is nu 3/4. So let me compute the Reynolds number. The Reynolds number is a typical velocity times a typical size divided by the viscosity. Typical velocity is 1, typical length is nu to the 3/4, and the typical velocity is nu, so it's nu minus 1/4, so it's still very large. And there is some beliefs that any shear layer is unstable provided Reynolds number is small enough, is large enough. So this sublayer can itself become unstable. So how can we look at that? So we will make a zoom, and this term we will make a zoom by a factor nu to the 3/4. And of course, the Navier-Stokes equation is now Navier-Stokes equation with nu 1/4. And so now I will make a zoom. So let us make a zoom. So I have a structure here which is square root of nu. So I make a zoom. So in the new variable, it's very large. So probably like, so it was nu 3/4. I make, sorry, so nu 1/2, so nu 3/4, so nu minus 1/4 probably. So it's very large thing. So now here I am in the sublayer. So Prandtl layer on the top and Euler layer on the top. And so I have very large things, and basically I have here something like an exponential profile. If you remember talk of Toan, then the boundary, this is explicit, and you have an exponential boundary layer. Of course, it changes, but with very long period in X. So what you can do is, okay, I freeze somewhere here. If I freeze X, then I have an exponential profile with a viscosity nu 1/4. So I will have nu 1/4 to the 1/4, so nu 1/16, which will appear. And I will have a critical layer somewhere, which will be nu 1/4, 1/4, so nu 1/16 in these variables. So if I look at the initial variables, I don't want to make a wrong computation, it will be nu to the 13/16, the initial variables. So in this case, three sides, square root of nu, and nu 13/16. How can it work? So this is a work in progress with Benoit Posader and Nguyen. The idea is, okay, you have a very slow variation in X, and you can control, if you froze X, then you can have an instability. So what you will do is a wave packet. So if you have some instability alpha, you have psi of alpha of Y, and you know that it's behaved like E alpha X minus C alpha of T. Yeah, this is that. And of course, you take, so the velocity is U equals that. So of course, if I fix some alpha and C alpha unstable, of course, it's OK for here, but not for here. So you have to localize it. And so what I will do is I will make a wave packet. So I'll make some profile B of alpha, B alpha, and I take B very picked around some alpha which is unstable. So I have if I look at the alpha, then I will pick some beta here, and I make a group of instability which are close together. So the interest of this is that it is very smooth in alpha, because I can take beta very smooth in alpha. This is smooth in alpha, this is smooth in alpha. The technical point is, of course, to check that it is indeed smooth in alpha. But the main point is U is exponentially decreasing in X. So when you play with sizes, then you can really construct an instability which is localized on areas which are very small with respect to nu minus 1/4. So you have a localized wave packet with a size less than nu minus 1/4. Okay, of course, it's not solution of linearized solution. You have terms which appear and so on. And so on. But the crucial point is that a wave packet moves with the group velocity. And so this moves the group velocity. And the group velocity is nu 1/2. So of course it's crucial. This works because the instability can appear before you move too far away from the original position. So you have a frozen X. At frozen X you have an instability. You construct a wave packet. It moves, but it doesn't move a lot. It almost remains in the same place. So you can iterate. So this is the thing that you are here. So let me just set a proposition, and then I will take the 10 minutes to discuss what has been done. So assume that you have US, which is spectrally unstable for Rayleigh, meaning that you have an unstable mode. Then there exists for every n and s arbitrarily large, there exists some forcing and solution such that initially in any space you are close to the initial data. So initially you are close to your initial profile. So your solution is close to the profile as will, such that the forcing term of Navier-Stokes is bounded by the same power. Okay, such that T nu is some constant log of nu and square root of nu, and such that u nu at T nu minus u0, so this was explained yesterday by Toan, is larger than some constant. So you are and such that u nu at T nu exhibits scales 1, of course, nu 1/2 frontal, nu 3/4 sublayer of frontal, and nu 13/16. We cannot go beyond that because if we try to make the next term, the problem is that because of what is here, the instability in this layer doesn't grow much. So when you are trying to do the next step, then the instability is too weak and you are not fast enough, and you can construct a perturbation, but it goes away and it has the time to grow before it crosses the previous one. So this is a main issue. If I look for stable profile, then because of the limitation which are here, we have just nu 1/4, and probably it cannot be more than that. And then we have only one layer, which is this one. So is there a question before I make some comments on that? So I will end by a few comments about the physics of that. But so basically the situation is a bit paradoxical, because either you prove physically relevant result or you prove mathematically. It seems that it's difficult to prove both at the same time. So the first one are physical relevant, namely things that you weight. We are waiting from Prandtl equation. You are waiting from boundary layer. So there has been a lot of work quoted yesterday, in particular by Kaflich, Sammartino, Maekawa, Masmoudi, David Gérard-Varret, who managed to prove that on that it's okay. Okay, for smooth data, so Gevrey or analytic, to simplify, and small time. So this is basically what we would like, because we would like to have a boundary layer, which is that. There are also work on vorticity separation and Lord Alibar, Nader Masmoudi, or blow-up of Prandtl like Nguyen and E, Björn and Quist, and of course previous work on this. It's a bit non-mathematical because you hide this result, hides the instabilities. Because of course what you get is that you have instabilities at high frequencies, at high spatial frequencies. So basically the instability of Prandtl occurs at frequencies which are very high, like 1/√nu, or even larger frequencies. And so what you have is something which is periodic with a very high period. This grows pretty fast. I mean, like 1, so standard. So basically, you have solutions which are highly oscillatory in X and grow 1 in time. Of course, if you look at analytic functions, then you put a weight in front of them, which is something like that. You put a weight in front of them, so you simply don't see them, because if R of t is like this, so then you see that R of t can decay lambda, and then you simply don't see the perturbation. So the perturbation is hidden by the weight you put on the analytic space. So if you are at initially you have a radius R0, then you don't see any instability till the time 1/λ. Understand that? So 1/λ. So basically you hide the instability. It's not so good. Then there is a mathematical result here. So previous result. Which so simply are spectral instability, so that's life. But for sure you don't want to hear of 13 of 16 layers and so on. And in fact, you don't find them in physics books. Basically, because what's important is the Reynolds number. In physics, you find books, you find diagram like that, which says that if your profile is, here you have the Reynolds number, here you have alpha, and here you have the unstable area, which means that, of course, people in physics know that for very, very large Reynolds number, if alpha is small enough, then you're unstable. So it's used there, of course. But what is crucial is a critical Reynolds here, which can be very large, like 10 to the 3, or 10 to the 4, or 10 to the 5, perhaps. And the successive instabilities, you see that first it's nu, then it's square root of nu, then it's nu 1/4, which appears in the computation. So you have instabilities where the Reynolds is larger than 10 to the power 4. It's okay. Reynolds to the 10 power 8, which is okay. But you see that to have the last phenomena, you have the Reynolds to the 1/4 to be larger than 10 to the power 4, with Reynolds more than 10 to the power, say, 16. It's going to be very large. So the phenomena you have here physically will only occur at unphysical Reynolds number. Of course, this happens, but for sure we will never make an experiment on the ocean in the stratosphere to see if you have a nu to the 13 over 16 layer. You have the turbulence, which is much before. So turbulence occurs much before. So the problem with that is that it's a mathematical construction that you can detail, of course. But if you look physically at Reynolds number which are involved, each time you go to the layer, basically you take the Reynolds to the power 2. And so very soon it's impossible to make an experiment. So of course the turbulence occurs before, and so you don't see that. So shall we perhaps combine the two? And I will just end with that. We have perhaps some open ideas. See, it's not formal, but let us to discuss what we can say. So we would like u Navier-Stokes minus u Euler minus U Prandtl to go to 0. So it's okay in analytic, algebraic, or if the vorticity is away from the boundary, so which is part of the physics is there for sure. But if we look at Sobolev, which is more natural, or L2, then you follow the fact that you have a cascade of instabilities occurring at non-physical Reynolds number. So you don't want to go to this area. So it's something like an endpoint. So what you like to do is to look at Reynolds which are large but not too large. So you would like to take the limit nu to 0 but not too small. Which of course have no meaning from a mathematical point of view, to say that you want to go to 0 but at the same time you don't want to go to 0. So an idea then is to try to make things more qualitative. Toan recalls that what governs the equation was the gradient of things. So you can try to say, okay, then if you have U Navier-Stokes minus U Euler minus U Prandtl go to 0, provided everywhere Prandtl layer is stable. So provided Prandtl layer is stable. So you can quantify by Reynolds number. Reynolds number of will be U Euler at the boundary. The velocity length is 1 over nu. So provided this is smaller than critical number. So provided this is smaller than a critical number. So this is the rest of the boundary, which is the value of U on the boundary, divided by the viscosity. So provided the Reynolds is less than that, then this goes to 0. So there's no meaning either, because when U goes to 0, we have that. But what you can try to prove is that this is smaller than some constant times square root of nu, provided by that. Of course, it still has no meaning, because you can have C very large, so it's nothing, but say till C equal 1 or 2, which will be some kind of qualitative stability result, which will be to say, okay, nu to 0, we are going to area of physics which are not what we want to do. Analytic is only small time, so we would like to have something in it nu to 0, but not too small, which of course has meaning, except that we can, okay, this and that will be valid provided the Reynolds number in the boundary layer is below some critical number. So the Reynolds the boundary layer is U over nu, which means that nu must be large enough, of course, but else it's unstable. That's nice. And of course, we cannot let nu go to 0, but we can put this down here. And of course, we cannot put C whatever we want. If we will put 10 to the power 15, and it's okay, but C to 1 or 2. Another way to look at things is to see that if you have a solution, then you will have a splitting minus 2 solution, Euler minus Prandtl, and Toan gives you a bound which is 2 gradient of U Euler T, and we can assume that if you have things like 1, like 1, something like that, you have the initial data, which depends on U Euler at 0, something like that. It could also be delicate to prove if Reynolds of T is less than the Reynolds critic, and the Reynolds of T is the subnorm of U and the boundary subnorm divided by nu. So it's a kind of result which says, of course, nu in practice this is large, to the power 4. In practice, the constant here are 1. So there is still something to do, because else we will have 10 to the power 4 in front here. and to see that if the Reynolds number of the boundary layer is subcritical, then the stability of the flow is controlled by what happens in the interior. So this is just some ideas in order to try to get something. This kind of result we have it for Ekman layers. Ekman layers have been done with Benoît Desjardins. But for Ekman layers, it's easier because if you take the speed of the rotation to be equal to nu, then you have here the speed of the rotation, and then this is more direct. Here we don't have that, so of course then we would like to get from a qualitative way to prove and that to a quantitative way, namely that this answer is true as long as there is no answer with a constant which is 1, not 10 to the power 15. Is there a question on that? Okay, so thank you very much for your attention.